Alright, we just walked through a simple linear regression exercise. We assume we have a linear model that is coefficient 3.5 and the intercept is 2. Of course, E here is some random error. We use this simple exercise just to illustrate some basic facts regarding what is called ordinary linear regression. The goal here is to minimize sum of squared and what's called residue. So we try to minimize the summation of this y versus prediction for n samples. If we were to do this, what kind of Python package to use? There are stats-focused, what is called statsmodels.api, and there's also scikit-learn, which is more popular for machine learning people. For stats major, you probably want to use stats model, where it gives you what is called a formula interface for you to define R-like formulas. So that's probably a preferred for some researchers. CS people or machine learning centric people is going to resort to what's called the scikit-learn, which is a set of machine learning ecosystem. And a lot of deep learning, AI, for example, if you're working with PyTorch or TensorFlow, is another ecosystem. You can provide a custom loss function, custom layers. You can build more complex models beyond the simple linear regression and the support GPU acceleration. So here, we're going to try to use stats models. In follow-up tutorials, we'll probably switch to scikit-learn or PyTorch if you move to neural network type of model. So for this exercise, we're going to use stats models package. So here we have the initial setup, that is to simulate the data by using a random number generator from NumPy here, right? We're going to set the seed so that when we rerun it, we have the same set of data points. We're going to generate 100 samples, right? And this would be equally spaced from 0 to 10. And Y is the true model here, assume we know, all right? And then generate the data using pandas. Now for the actual fitting here, you can use the package, adding constant term for the intercept, and the model would be what is called OLS, the ordinary linear regression. And then you call fit, and then the model will be generated. When you do the extract the predicted value, which is the data here is predicted, the model summary will print out interesting stats. Now this is very comprehensive, right? Now some of the value you probably learn is kind of R-square that measures how much variance your model can explain, and this calculated to be very high, so which means the model is good. And there's F statistics, that's for statistic test. It's very useful if you have multiple variables. In our case, it's a single variable, right? So F stats and some other quantity that we probably don't care too much. There is some explanation here, right, from the package. And in our case, we find out that the variable, particular variable, is a strong and a significant predictor of dependent variable, right? So the slope and the intercept, okay? When we plot the results, so the blue dots are the samples and the red line is the prediction line. RSS, the residue sum of squares, right? Just do the sum, this is square, right? The sample value, the predicted value, right? So that would give you RSS, right? And the error variance here is divided by n-2, which is the degree of freedom in your case. And so error variance is about this, okay? So usually for linear regression, you want to calculate what's the confidence interval for the two parameters, beta 1 and beta 0, right? The slope and the intercept. Now, in order to calculate confidence interval, you should know the standard error, right? Standard error is a formula, so we plug in the formula here, right? And here we have the results, right, for two different parameters. And we'll try to find a confidence interval here. We use what is called the t-test, all right? So that's the different lower bound and upper bound. And for the coefficient beta 1, here's the slope is 3.4 to 3.6, 95 confidence interval. Of course, since we created the model, we know that the true value of the coefficient is 3.5 earlier, right? The intercept is 2. Okay, so here there's a brief explanation why we use t distribution in the regression analysis here. Z critical or t critical here really slightly different value for 95 confidence interval, right? So here's the comparison is that one is 1.95, sometimes we said 1.96, right? And here would be 1.98 for t, right? And there's a useful function here called ppf, right? A percentage point function. So area on the curve up to x is p, right? For example, 0.5 for the normal distribution, you would have 0 here. So the elective value is going to be add up to 50% of the PDF, the probability density function. It is essentially the inverse of the CDF, this PPF function, right? Very useful, right? So that's just a simple walkthrough of the linear regression, and the understanding of some of the metrics is just for a simple model, simple exercise. Come back for more complex model in the future. I will provide the link in the video description so that you can download the Python notebook and run it on Google Colab or your own environment. For these and other math or computer science topics, please like, share, and subscribe to the channel.